Okay, so I'm here. What we're going to do is run through a couple different activities or a couple different labs that we're going to do in the class. I wish that I could have you do some of these. If you have magnets, you can, but otherwise, at least I can show you what's going on and or what you're seeing and kind of walk you through with that. So the first activity is the one that is just playing around. So I have this bin of junk that I have a bunch of different random things in it. So I have some manila folders that I cut up. I have a piece of plexiglass that's in here, a protractor that is my plastic. This is a hard drive out of an old computer, a wire, a battery, like an L brace, a refrigerator or part of a refrigerator magnet, and then a horseshoe magnet and a regular magnet. And the whole goal is just to play around and see what is magnetic and what is not, and a couple different things too, like can I take, if I have a plexiglass here, can I shield that magnetism so that it's not affected? And what we find as we play with these is there are several different observations we can make. The first observation being that we can't really shield that magnetism very easily, at least not with any of the stuff that we have in here. That magnetism, those magnetic field lines work through the other objects. The other things that students may notice as they're doing this is that anything that has electricity, it's affected slightly by the magnetic field of the magnets. Or some of the really gun-ho students may notice that if they connect this into a circuit so that we have the flow of electrons, that will actually cause a magnetic field around the wire. So one of the other things that I don't see in here that is normally in these bins is a really small compass. And that compass they can place by the wire and see that there's a magnetic field from it. So that is the first activity, and that is just taking around and playing and getting different observations that we have based on the magnetic things that we have. So for this activity, I wanted to show you the magnetic field around the magnet. So we have our magnet here, north and south, and notice that each of the compasses are following out these different rows of the magnetic fields around the magnets. I'm going to take then and show even more so. So I put a piece of paper here, there's a magnet under the paper, and then this is just iron filings that I'm going to sprinkle on top of the paper. And as I sprinkle those on, hopefully you can see, with all the shaking that I'm doing with the camera, can you see those magnetic fields also all the way around those magnets? So it comes out the end, goes all the way around, and comes back in the other end. It's strongest at the poles, so you can see that the most filings have gathered right against the edge of the pole there, and then they go out one side and in the other side, and that's demonstrating the different magnetic fields. The next thing that we would do then is I would take this, and we're going to do the exact same thing. I'm going to just shake some of all that down and do it with a horseshoe magnet, so you can see how the magnetic field looks like on a horseshoe magnet. So there's my horseshoe. Pardon the shaking again. Here we go. There you go. So you can see in the horseshoe magnet that the magnetic field comes straight across from the two. So this must be one pole and this must be the other pole, and then it gets weaker as you get down into the end and you get sort of these random magnetic fields down there. But the same thing, it would come out the end of the pole and connect to the other one, come out and connect to the other one, and go around like that. So that's how the magnetic field looks like for a horseshoe magnet. So in this demonstration, we're going to take what is called a bitter fluid. And all it is I took an old print cartridge that it said my ink was gone. I ripped the cartridge open and scraped out the leftover ink that was in the bottom of the cartridge. And then this is just rubbing alcohol. And the reason we use rubbing alcohol is because it evaporates really quickly. All this is then will be these, we got these from the university housing at a special event that we were at to demonstrate this. And this is a magnetic barcode that you would use to like swipe your door open. It would also be like old credit cards have these. And so what we're going to do is we're going to take this bitter fluid and we're just going to put a little bit of the bitter fluid all the way across here. And remember that we picked the rubbing alcohol because it dries very quickly and very easily. So we'll come back in a second or a couple minutes after that's dried, and I'll show you what that looks like. So while that's drying, I want to show you the last activity that we're doing. All this is a refrigerator magnet, so you'll notice that there are magnetic pieces to that I could take this on the fridge, and I cut a strip, the vertical strip here and a horizontal strip here. And what we would do with this is we play around to try and figure out, well, where is the North Pole and where is the South Pole on our magnet? So as I move this across here, I notice that nothing happens. As I move it across there, I notice that nothing happens. But if I move it across that way, can you hear the snapping to that? So something is going on with it that way that doesn't go on this way or this way, right? And again, if I take this guy too, if I move it, you can hear the snapping that way, but you can't hear the snapping that way. So think through if I can, I don't know if I can get this to show here very well, but when I push it there, notice how it pops out, pops in, pops out, pops in, pops out, pops in. Doesn't that mean that it's attracting, repelling, attracting, repelling, attracting, repelling, which means that there's not just one north or south on this magnet. There have to be a whole bunch of norths and souths, and they all have to be kind of in a row. So if I were to draw the magnet, so here's my magnet, coming around, draw my magnet here, then as I'm pushing this up and down and hitting those, then it means that there are going to be rows of norths and souths here, where this is like north, 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 south, 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 north, 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 north. And again, as I cut this piece off and I'm moving up and down those north and norths, when the north is on the north, it's repelling. When the north is on the south, it's attracting. And that's where you get that sound from that. And that's why these will stick really well to your refrigerator or whatnot, because there are a whole bunch of different norths and souths, and that combines together to put them onto to have a good magnetic field. Okay, so coming back to this guy, I'm going to come in and see if we can catch the glare in this. Can you see, if I get on the glare just right, can you see the magnetic barcode or the magnetic bar strip that is right there across the key card? And so what's happening is there's that bar there, and when they swipe this, it sets it temporarily, and then the doors read that temporary barcode that's a magnetic barcode, and then that's one of the reasons why they're so easy to mess up. So like a lot of hotels will say, well, don't put your room card in the same pocket as your cell phone, because the magnet in the speaker of the cell phone will erase parts of this barcode, and then your door key won't work whenever you go in. And remember, the whole reason this works is because way back when we studied the electrostatics chapter, remember that we said the printer cartridge ink is electrostatically charged. So because it has those electrons in it, that really, really, really tiny molecule of the ink can become affected by the magnetic fields. And so it's actually affected by the magnetic field of the barcode. And then when the rubbing alcohol evaporates, it leaves that really small piece of ink in the shape of whatever the barcode is from those. And that is the bitter fluid. So in the first part of this lab, what we're doing is we're looking at these disc magnets that look like this. So it's just a magnet that has a hole in. We're trying to figure out the north and the south, and if I put them by compasses, you'll notice that the north, it doesn't do like north and south like this. It does north and south on the sides. So if I take and put my disc smack in the middle, notice how it causes the compass needles. And then if I flip it, notice how it flips the compass needle. And then it wants to turn back again. How it flips it, because it's being affected by this guy over here. If I flip it, it flips those compass needles. The next part of it, what we're doing is we're taking 3 of these disc magnets and we're looking at a magnetic field sensor. So if I stick the magnet up here about maybe 2 centimeters away from the sensor, notice that it has a field of roughly 0.9 milliteslas. Well, if I take 3 of these, how about we start with 2? If I take 2 of them and put them about the same distance, notice that that's gone up to 1.6 milliteslas. And if I take 3 of them and I stick them up here, notice that that goes up to 1.8 milliteslas. So or if I put it back closer to where it was, then that goes up to 2.4 milliteslas. So that magnetic field adds up from each of those magnets and makes it stronger whenever they are together. So with them all together and at about that distance, you'll notice that it is roughly 2.8 milliteslas. And what I'm going to do then is I'm going to take and flip my red one so it's going the other way, and I'm going to have to force them together because they don't want to be that way. And if I stick it at roughly the same spot again, then notice that that has gone down because those magnetic fields are canceling each other out. So the fields, remember that the spinning electrons are what cause magnetism, and then domains are clusters of spinning electrons, and we're modeling that on a much bigger level now where we would think of each one of these as a domain. And so if they're all acting together, it makes it stronger, and if they're all acting against each other, it makes them weaker. In the second half of this activity, what we're going to do is take a nail, and notice if I put the nail next to these guys, nothing really happens. It's not very magnetic. But if I do bring it near the compasses, it does change the compasses a little bit. So what I'm going to do is I'm going to drop the nail a couple times just so that it demagnetizes anything that is magnetic in it. And again, I'm going to just bring it next to that. So that's jarring all of those domains, and the domains are loose enough that it'll reshuffle or randomize those electrons. So what I'm going to do then is I have these really strong neodymium magnets, and then I have my nail here, and I'm going to rub the nail or stroke the nail in one direction so that it helps to magnetize or remagnetize those parts of the nail, the different domains that are in the nail. So then I should be able to come over and notice how it picks up one of the staples because now it is magnetized, and there I got two staples from that. So theoretically, the more I would stroke the nail with the strong magnets, the more domains I would align and the stronger the nail would become. So this would be sort of a semi-permanent magnet in the fact that we can demagnetize it and remagnetize it based on whether we can get those domains to line up or not.